So the next speaker is Soojung Young. She is a fifth-year PhD candidate at MIT. So, yeah.
Why?
Yeah.
No, just. Hi, I'm Soojung, and I'm a PhD student at MIT. And this work I want to talk about is done in a collaboration with Microsoft Research, where I did my internship last year and then contributed to bioimmune project. So first, the title of this workshop is includes generalizable model. So maybe we can think about what is generalizable model and how to achieve that. So we can train a property prediction model for each property. Maybe with protein stability data, we train a model that can predict the stability from sequence. And we can train another model trying to predict co-folding structures or binding affinity. Or what I call foundation model is basically it's the hope of if we throw a bunch of all the data that we have in one model, then it'll learn something generalizable so that it can predict different properties at the same time. And bioimmune is in this line of research, in my opinion, but we have one more thing in the middle, which is conformational ensemble. And this is in a hope that, because ensemble is something physical, something that has physical reality, the model will have more interpretability and maybe could be more generalizable when we try to use this model to predict properties. And this is a hypothesis that I want to propose. For each data, we have unique solution space. So for example, when we train machine learning model, because it's not like based on physics, it's just black box parameters. Those parameters can mean anything. So there can be several different solutions for one problem and one data set. But if the same model has to solve many different problems at the same time, then maybe the common solution space in the overlap could be the most generalizable solution. And maybe because the most generalizable solution is physics, maybe it will start to resemble some physics. So for example, if a model is trained on all the different type of data, like protein structure, thermodynamic, observables, global or local properties like electron density, NMR chemical shift, like all of them, then maybe the model will be more generalizable. But for bioimmune, we kind of try to test this hypothesis by using two different set of data. First is structures from MD simulations, from PDB database, from AlphaFold database synthetic data. And then with this very high resolution optimistic structure data, we train generative model so that it can sample the ensemble. And then we had another very different set of data, which is experimental experimental stability. It was high throughput delta G measurements of many proteins and mutants. And this delta G value, it just gives us the global ensemble statistics. In easy way, it's ratio between folded and unfolded states. But we try to see if we can combine these two data in a very different resolution to train a single model. So as a result, the model could sample structural ensemble, and then it could predict this global ensemble statistics called folding stability in a good ground truth prediction correlation. And then what was important for us was that combining these two different resolution of data, the model could learn some high resolution structure stability relationship. So for example, here, these are different mutants of the same wild type family, and they have different folding stability. And like this graph shows that what happens to the structural ensemble when we make a mutation. And then here we could see that we could come up with some explanation like, okay, this mutation creates this change in structure, and then that leads to some folding instability. Now, as a follow-up project after BioEmu, I started working on developing temperature-dependent version of BioEmu, because temperature is a very important parameter for that governs protein function and ensemble. So if we have a temperature-dependent ensemble sampler, then we can predict thermostability, we can predict temperature-dependent behavior of proteins, we can estimate thermodynamic observables, and maybe we can use it for enhanced sampling of some states that are hard to see in lower temperatures. And here we bring another type of data. We have a large deposit of protein melting curves in ProthermDB, but most of the data is not like immediately suitable for machine learning model training, because they are very like all the entries come from different experimental method, different denaturant, different experimental condition. So there was effort to clean up this data set to find a reliable and consistent set of melting curves, which is Scoop dataset and Hot Music dataset. And here they report melting temperature and delta H and delta heat capacity. And from these variables, using Gibbs-Helmholtz equation, we can plot the melting curve, which is basically delta G that is temperature dependent. So we trained BioEmu with these melting curves following this protocol. So starting from the pre-trained BioEmu, which doesn't have any temperature dependency, everything is supposed to sample from room temperature. We add temperature condition to the model, and then we train with melting curve. And because the proteins in this data set, melting curve data set, we didn't have MD simulation data. So only structure data we had was crystal structure from PDB. And we assigned this crystal structure to the lowest possible temperature. And then we train with melting curve for both wild type and mutant. And then we also supervised the model with delta H at melting temperature, which is basically the slope of this melting curve. So this is, now I have to explain how can we, like training generative model with samples is, it's trivial, but training generative model with ensemble statistics is not. So this is the method that we developed. It's called PPFT, Property Prediction Fine Tuning. And this is the way of, if the only information we have about the ensemble is some statistics like folding stability, then how would we like backpropagate all this information to the parameter and train the model? So how we do it is the architecture of bioemu is diffusion model. So we do denoising, and then we obtain the final structure. And from this final structure, we compute foldedness with some classifier. And then this ensemble average of foldedness is directly connected to experimentally measured folding stability. So we just backpropagate the difference. And with this loss, using this learning objective, the correlation between predicted and experimental folding stability has become much more better. And this is the specifics. So here, there are two tricks. First thing is this loss function has to be differentiable. So the classifier cannot be binary. Instead, we devise this smooth foldedness function based on collective variables like DRMSD or fraction of native contacts, and which gives us, roughly how folded this structure is compared to by comparing it to native known folder structure. And then the second trick is we need to compute the ensemble average, but when we train machine learning model this large, then it becomes very memory intensive to have a large batch, and then compute average, and then use that one signal to, backpropagate all the way. So here we use a very small batch size. We can use batch size of 2, and it empirically still works, surprisingly. And how we do it is, so we compute foldedness for each sample, and then we repeat it twice for each batch. And then we use this loss term to close the distance between the target foldedness based on experimental folding stability versus this sampled folding stability. And then to better train temperature dependency, we added this one more loss called derivative loss, basically made to supervise with delta H at melting temperature. So with some steps of approximation, delta H can be written like this, which is the derivative of foldedness with respect to temperature at melting temperature. And this derivative, we can compute it with torch autograd. And as a result, our model shows good transferability for both melting temperature and delta H prediction. And this result is for the wild types. And here, what I mean by predicting melting temperature and delta H is not that the model directly outputs the numbers. The model outputs the conformational ensemble given the sequence and temperature, and we sample for multiple temperatures. And then, melting temperature, it's obtained by, finding the temperature that gives us 50-50% percentage of folded versus unfolded structures. And then delta H is obtained by taking the derivative at melting temperature. So here the experiment was 8-fold cross-validation. And then in this original data set of 222 proteins, I cut off a lot of sequences based on maximum sequence identity 40%. So in this small data set of 65 proteins, there was no pair of proteins with sequence identity more than 40%. And I divide the data set into 8-fold and then do cross-validation. And the first plot is the training set, and then the second plot is the test set. And then the third plot is correlation of experimental versus our model's delta H prediction for the test set. And these are some melting curve predictions of our test set proteins. So the model has never seen those proteins, but the agreement between prediction, which is red curve, versus experimental melting curve, which is black curve, is pretty good. And then using the mutant data set, we also trained the model with mutants. And here, mutants, even though it's a little bit, it shows similar correlation with the wild type case. And what's surprising is the model has never seen any mutants of 1BVC, but still it figures out which mutations which mutations improve thermal stability and which mutation does not. And this is an example of mutant family of 2RN2, which is E. coli RNase H. And here, I just wanted to show that measuring delta G at fixed temperature might not be enough to predict thermal stability, because there are all other variables like delta H is also temperature dependent, mutation dependent, and even though they have similar delta G at room temperature, they might show very different behavior at other temperatures. And here I want to reconnect to my beginning slides of whether these adding a lot of different heterogeneous data will result in model being more generalizable and maybe like figuring out some physics. And this is one example of what our model is doing. So for this same 2RN2 mutant family, this is experimental melting temperature versus predicted melting temperature of the mutations happen at residue number 52. So these are mutations all at the same spot, but to different type of amino acid. And here the prediction is quite promising. The model correctly predicts hydrophobic mutations as more thermostable, and then charged or polar mutations to be less stable. And this agrees with this experimental result, which provide this data set of mutations at 52. And in this paper, they experimentally found out that because this mutation at 52, which is the yellow spot, is in its folded form close to interacting with this red spot, which is hydrophobic. When we make the mutation hydrophobic, then it improves the stability. And here, we can try to, because our model does not just predict the thermal stability value in like numbers, but instead it generates the ensemble. We can try to see if that's actually what's happening. So here, these are the distance map. These are the distance map difference between mutant versus wild type. So from these figures, we can only see what the what kind of effect this mutation is making. And here, 5 to L and 5 to I, L and I are both hydrophobic residues, and then they have this red spot in the middle, while polar residues like H and N, mutation does not. And what that red spot is telling us is that the distance between mutation 52 and this red hydrophobic area has become smaller when hydrophobic mutations happened, which is what we expected. And if we bring the same analysis at lower temperature, where most of the proteins are folded anyway, we don't really see very clear difference between hydrophobic versus polar residue. So this can be a hint of why we need temperature-dependent experiments and modeling. And also, this plot is not only mutations of 52, but all the different types of mutations. We see good correlation. And then if we do the same analysis with different type of mutations, we see some local interactions changing. So here the blue lines are at 23. Here the blue lines are at 62, where the mutations is at. And we can see that like this structure, local interactions, they change in the proxy of where the mutations happen. But not only there, but also other parts where the mutations can affect structurally. And this part is trying to see if our model can correctly predict local delta H of opening. And here in this example, in this literature, we have experimentally measured temperature-dependent hydrogen-deuterium exchange results, which directly give us this peptide-wise delta H. And then I show the result from this experiment in blue curve here, and then result from our model sampling in orange curve. So it kind of agrees well with each other, except for this peptide number 3, where our model has very high delta H, and then the experiment shows very low delta H, which means that in our samples, this peptide number 3 is always folded and never, always closed form and never opens up, while in experiment it opens up, much more frequent and quickly as temperature rises. But it turns out that there is a bias in our data because our data use PDB X-ray crystallography structure deposited as our training data. That data had this cofactor bound peptide 3, while this experiment was done without this cofactor binding. So with this cofactor binding, this part, peptide 3, have become much more rigid, and then delta H becoming really high. So this is one example of the limitation of the current model, that there is a lot of bias in the data. This example is showing an advantage and limitation of our model at the same time. So in this ribonuclease H example, there's two forms, open and closed form. These are local conformations, and they are both related to enzymatic activity of this enzyme. And then this experiment tells us that for this ecRNH protein, there is temperature dependency of relative population of these two states. And these two states are, the collective variable here is handle distance between those two key residues. And then when we sample this protein with different temperature with our model, we exactly see the two peaks that was found in experimental study. However, the trend is the opposite. So here from the experiment, lower temperature shows more open form and higher temperature shifts to more closed form, but our model's prediction is the opposite. And this is one limitation because our model, of course, from the hypothesis that I proposed in the beginning, if we add a lot of global statistics, global signals, maybe there is like the only way to learn all this global signal is to learn the local behavior correctly. But sometimes that's not the case. And sometimes because we only train with global folding and unfolding instead of local open and closed data, this can happen. So here, one advantage of this approach is we can change temperature and then do some kind of enhanced sampling to get the previously hard to observable states. But it also tells us that the data that provides accurate local signal is required for further development. This data can be something like hydrogen deuterium exchange results or any kind of temperature dependent observations. So that's in the future work. These are the people who are contributing. And yes, I work with Rafael Gomez-Bombarelli at MIT and Frank Noe at Microsoft. And this is my email. Thank you.
We'll open up the questions. Use the neutron diffraction data with
Neutron
diffraction data.
data.
Structures in the PDB that you report relative amounts of HD exchange and at that point.
Oh, I was not aware of the data. Yeah, I'll take the notes.
Take a look.
Yes, thank you. Wait. So yeah, my background is machine learning. So I came here to learn a lot about experimental data from you guys. So,
I have a question about fine-tuning the genetic model with ensemble statistics. Like I'm thinking this that like you are supervising the distribution with single like first order moments. Like how can you prevent overfitting?
yes. So at first we were worried about that. So we froze a lot of layers. And then later we found out that that's not even necessary. We just have to use very low learning rates. And then another trick is, so here, because we need to compute the property of, for the clean sample, we do the rollup denoising all the way, and then compute property, and then like backpropagate the loss. But we only backpropagate few steps, not every step. So for some steps, we just turn off the gradient. And that I think that helps with this overfitting issue, because we are not like trying to change every step in the denoising.
Any other questions?
I have more kind of general questions about your prediction of the temperature melting. So, AlphaFold 3 and 1, 2, whatever. When the low confidence is like the PRDT values in prediction of the parts of the molecules are low, it's most of the time because A is unfolded or B, there is no evolutionary trace. So there is no sequence alignment MSA properly done because there is no sequences structures available. Did you ever try just take those bits, peptides, they have the low PRDT confidence in AlphaFold or any kind of AI prediction and compare what's the temperature melting points are on those? It would be nice correlation to see how the real AlphaFold predictions correlate with your.
So here the assumption is if there's a lot of flexibility in the data, then it'll result in higher PLDT.
Yeah, but sometimes the high PLDT value is not because of the flexibility, it's because the sequence, there's no evolutionary trace of the sequences. They don't need to be flexibility. So just test exactly what you just said. Is the flexibility or it's just missing the sequences in the training?
Yeah, that could be interesting to see.
We have time for some more questions. Yeah, Doris?
You mentioned this one case where you find that some data in the training are that kind of biased, where, like because the cofactor binding that kind of prevented predicting this unfolding. I'm just kind of curious, has that kind of inspired like a more systematic approach of how you address these issues? Like I would imagine it's pretty bad to whenever you find a failure case, you go back and try to correct that.
I think the ultimate solution is to make a all-auto model that models cofactor and solvent and everything, every like experimental conditions. Because here now it's a confounding factor. Now our model is not all-atom, so it cannot like consider any cofactors. That's why this kind of things happen. We cannot condition on cofactor, but eventually, as we collect more data and as we develop our model architecture to reliably and effectively account for all atom structure, then yeah, could be better.
Very cool talk. I was wondering when you do the property prediction fine tuning on these temperature dependent properties, do you see it start to perform worse on the original stability data fine tuning? And do you, I guess, have you explored that at all and seen, is there a way to try and balance this so that it is more general on both of these data sets? To try and get more towards the center of the Venn diagram you're showing.
Right. That's a good point. I haven't tested this setting on the room temperature, so that like we see whether the model still keeps predicting delta G at room temperature correctly. But like those two set of data should be compatible to each other in theory. So yeah, I can imagine like just adding a loss term to supervise on this delta G at but actually we're doing that because here in our training we sample temperature randomly and then we obtain this delta G at that temperature from this melting curve and then train the model on that. So the model has been seeing this same delta G at room temperature during our training. So but that's something we should do for sanity check.
I guess also to clarify, is this model trained from the base model? So is the temperature dependent model trained from just the original model pre-property prediction fine tuning, or is this post the stability?
It's post.
Okay.
Yeah.
I see.
And that makes a huge difference. Yeah, we like this kind of training is very, very sensitive. So we need to make sure we start from a good point. Like even this mutant training, it has to be trained on top of a model pre-trained on wild types, because otherwise, yeah, it just like becomes too unstable.
We have time for maybe one more question.
So, I think that there's like a variety of different experimental, both like structural, new data that we need, but also clearly functional information. And from your initial sort of look into this, if you had to sort of prioritize different things, if it's like, more, the DHFR, right? Having no, cofactors, or you need different ligands, or is it more of that you need more diversity in the data when it comes to the stability measurements? Like where are you pointing at sort of how the prioritization, if you were to choose, of the experimental data that's chosen at this point?
That's a great question. So for this enzyme example, like DHFR, we just assume that this global folding unfolding would have some correlation with local opening and closing. That could be true for some proteins. That might not be true for some other proteins, because global folding unfolding behavior can be, the mechanism can be very different from local. So you're right that like we need to maybe first choose the application, whether we want this model to model this global behavior or more of a local behavior. And then we can think about what kind of data is necessary. But like how I think about this currently is because the data we have is so scarce, let's see what data we have and then start from there. And this trying to train a melting curve is based on that approach. And if I can have unlimited source of data, then I think I would say temperature dependent HDX, because maybe it's not like a very old consensus, but there is more evidence trying to relate this local enthalpy of opening to enzyme activity, because it is related to, because most of enzymes are thermally activated. And that enthalpy is, there is more evidence of that enthalpy being related to reaction rates. So that could be interesting.
Thank you, Soojung. That's a great talk.